Good day, everyone. Thank you for joining the webinar. My name is Mike Dillon. I'm with the Mobile Shop, and we're going to talk today about accelerometer design and theory. A little bit about my background is I started as a accelerometer designer with PCB in 1994, and we started a product line in Cincinnati. Moved it into manufacturing in Depew, New York at the headquarters. And 5 years after I started, I moved it to the Mobile Shop to do application engineering for calibration systems and instrumentation. And as it turns out, in 2004, after 10 years with the company, I left for 9 years and returned to the company in 2013, back to the focusing solely on calibration systems. And this series of webinars starts off with accelerometer design and then moves into calibration techniques and calibration theory and topics. So we're just getting started with this series. But before we start talking about calibration, we're covering accelerometer design first. And to do that, we'll have an agenda today. We're going to cover the common types of accelerometers that will come through a calibration laboratory. We'll talk about the electromechanical design, the characteristics of those electromechanical designs, the applications we use the different types of accelerometers in, and how they're made, the construction. And finally, we wrap all those things together to talk about why those different characteristics and how those characteristics contribute to selecting a reference accelerometer that we'll use in the actual calibration technique. Okay, and that's how we wrap it up. So, accelerometer types, the most common ones we see today on the right-hand side is a list of accelerometers that are not very common. They're more inherited from our legacy over the 50 years we've been in accelerometer design. More commonly are the ones on the left, and we'll talk about these. The resistive, also known as strain gauge, thin film, or piezoresistive. Capacitive, also known as micro-machined or silicon wafer type. And finally, piezoelectric. And those are the three that we'll go over in detail. The other ones on the right you'll see are things that you may see in the literature and from years past, or it's probably rare that you're going to see those come through a calibration lab. Things like slide wire potentiometer, that's also known as LVDT. That's not so much a vibration device, it's more of a low frequency displacement. Variable inductance, that might be a voice coil type of accelerometer. Those might come through, we still see those, but generally speaking, the ones we see on the left are the ones we're really seeing on a day-to-day basis. And they have certain characteristics that have just made them more popular and basically technically, in a lot of cases, technically superior as their cost has come down over time. Okay? So the resistive design. We'll look at the schematic for this resistive type accelerometer first. The first thing I'll point out is this. On the right, toward the right-hand side of this diagram, we have a mass, and that's an inertial mass. And that's a common element that you'll see in all of these accelerometer designs. And we just use that inertial mass in different ways on the transduction side as we convert that mechanical energy into an electrical signal. So to the left of the mass, you see extending to the left is a cantilever beam. On the bottom of this diagram is the structure, is what the mounting surface of the accelerometer that's mounted to the structure. And what we're doing is we're measuring mechanical motion of that structure, and we rely upon that base of the accelerometer to be securely attached to the structure. And then when it moves vertically up and down, the accelerometer housing moves with it, and that inertial mass tends to stay in the same place due to its inertia. And as it tends to stay in the same place, it causes deflection of the cantilever beam, and that deflection causes strain on the top and the bottom of the cantilever beam. And you see there in the middle, almost in the middle, we see those variable resistor symbols, and those are indicative of strain gauges, variable resistive, basically variable resistance type elements that we use to measure the strain, not directly measure, but they provide a change in resistance due to that strain. And those are assembled into a Wheatstone bridge, which is probably recognizable by most of us when we see the two resistors on the left-hand side. So it's a full bridge. And what we see is the change in strain on the right-hand side can be measured on the output connections of the Wheatstone bridge, while at the same time we're applying power, excitation voltage, a DC excitation voltage usually, to the other side of the bridge. And that is the basic concept of the piezoresistive, aka resistive type sensor. The next diagram, we see this is what we call a capacitive type device, where we, instead of using strain, again, you see on the right-hand side, the green element there is another inertial mass. Again, it's that consistent element we have in all these. And while the cantilever beam extends to the right, we're not using that cantilever beam for its strain characteristics. We're instead placing that inertial mass between the two blue plates, and those are designed such that they have a specific capacitance in the air gap between the inertial mass and the plates. It's the same concept that when the base of the accelerometer moves up and down, the inertial mass tends to stay in the same place, but rather than the resistance changing in a strain gauge, we see the distance change between the plates. And that change in distance between the plates causes a change in the capacitance across those plates. And when we apply a constant voltage to it, we can measure that. Actually, that change in capacitance causes an output voltage to appear on the output of the accelerometer. And again, this is typically implemented in what we call a MEMS, microelectronically machined device. And it's in silicon in very small pieces. And we see down there at the bottom, the electrodes of the capacitors are spaced at thousandths of an inch, 1/1000th of an inch, or 25 micrometers apart. And that's the second implementation of this inertial mass. And then finally, what we'll talk about is the characteristics of both the resistive and capacitive. They have similarities when we talk about the spec sheet that you'll get from an accelerometer manufacturer. And the first one is really the most unique, is that it has the ability to measure DC. And DC is an electrical term, but in mechanical vibration terms, it's 0 hertz acceleration, which is another way to say gravity. Okay, so what we have is the ability to measure directly gravity and get an output of these accelerometers in a gravitational field, so that if we turned it immediately on its side, we would get 0 output, and we could get full output if we put it right side up. Okay, and that's not the case with the other type we have. We actually require measurements. So there are certain applications that works really well in for low frequency measurements. That's a really positive type. That's a really an asset to a measurement engineer, is to measure that 0 hertz on one hand. On the other side of things, it has what we refer to it as a limited dynamic range, relatively speaking, to the piezoelectric device that we'll talk about later. And that's 80 dB, 80 decibels, or a 10,000 to 1 ratio dynamic range. And when we say dynamic range, it's the ratio of the max output of the sensor, the max linear output of the sensor, to its noise floor. So in this case, what you see is that 10,000 to 1 ratio. That would imply that the accelerometer could measure up to 10,000 Gs and have a 1 G noise floor. And then by the noise floor, for this discussion, we'll call that the lowest acceleration level that is measurable by the accelerometer. So there's inherent noise output, and we don't want to measure noise, we want signal. So more signal is another word for more dynamic range, And you're going to see about a 10,000 to 1 dynamic range. And that's all, AKA also 80 decibels if you convert that from a ratio to pure decibels. The high frequency, now you've got in that first bullet, we have the 0 hertz capability or low frequency ability, but on the high frequency range, it's rather limited. It's going to be below 10 kilohertz. That's a drawback. And then the other thing, and this is kind of a more of an awareness thing. It could be used to a measurement engineer's advantage or disadvantage, is that the sensitivity varies with the excitation voltage. That's not mechanical excitation, that's electrical excitation of the sensor. You may recall that we had a Wheatstone bridge that we discussed on both of those designs. And you may remember about Wheatstone bridges is that if you apply twice the excitation voltage, you will invariably get twice the output. And that output directly affects the sensitivity of the accelerometer. And it's expressed in millivolt. You'll see the term millivolt per G per volt, right? So a sensitivity of an accelerometer is expressed in millivolts per G. So we may get 10 millivolts per G, but that's at 1 volt excitation. And if we applied 2 volts of excitation, we would expect to get twice that sensitivity. And another characteristic that if you see an accelerometer with a multiple wire interface, the 3 to 4 wires coming out of it, and you'll see them in what we call a tinned lead or a pigtail type connection where they have bare wires coming off. There may be a bound cable for multiple meters of length or multiple feet of length, but they terminate in a lot of times in a tinned lead connection where it's just bare wires. That's a pretty good indication when you look at the accelerometer from across the room that it's a bridge type device, either resistive or capacitive. Bridge in the case of resistive accelerometers. Capacitive, that second to last one doesn't really apply to the capacitive devices because frequently, especially the ones from PCB, they'll have internal voltage regulation so that the operator can apply a range of excitation voltage, a really broad range, just say something like 2 to 20 volts in the internal regulator of the accelerometer deals with any variation so that you get a constant sensitivity of the capacitive accelerometer. All right. So what they're used on, these are typically used, we like automotive applications. More abstractly, we'll talk about long duration, low frequency events. More concretely, we talk about automobile acceleration, deceleration, like road testing, real vehicle testing. Sometimes in aerospace, they'll be used on modal tests where they need low frequency response. Again, road response, robotics. So there's actually is an application where these are used to actually control motion of robotic arms and limbs. And whole body ordnance testing, that's impact testing that we get in a lot of military applications where they're measuring the effect of the ordnance or explosion device on whole body. So those last 2 bullets that you see there are both effectively crash dummy testing, but we usually talk about crash dummy testing in the automotive applications where the military folks talk about whole body ordnance, and they have their whole body crash dummies, and they place those in an event, an explosion event, due to their particular ordnance. Another one are tilt sensors. Those are tilt sensors. These are the sensors, especially the capacitive ones, the MEMS ones, we find in our phones all the time. Those have the ability to measure whatever direction our phone happens to be tilting, and they need that low frequency DC response for that. And finally, airbags are very low cost ones are used in the airbag industry because they're not measuring in an airbag event. It's not so important to measure micro G resolution between events. We just need to know when there's a massive event, and then to really, with incredible reliability, measure that effectively and deploy the bag. And finally, the final type of accelerometer we call a piezoelectric accelerometer. And this is an entirely different design. And what we're seeing in this little animation on the right, we call that self-generation. And that's unique to the piezoelectric accelerometers in that as we apply strain, it's still that element of strain that we had in the other ones. We're straining, but we're straining a crystal. And this crystal, it could be quartz or ceramic, when it's deformed, the crystal lattice structure is such that it electrically polarizes it on opposite sides. And you see the charge gathering on the left and the right of this gauge, or the left and right of this crystal as we compress it and relax it. As we compress it, it gathers. As we relax it, the charge tends to fall back. And again, we get that strain output. We get an output relative to the strain, and then we introduce that same element, the seismic mass, that tends to stay in one place, and that acceleration of that mass, that inertia of that mass, induces a strain on the crystal that causes that deformation. And you see we get a change in voltage across those plates as it does that. So what it looks like, I'm getting more of an illustration type here, illustration type of diagram, this is a piezoelectric accelerometer cutaway illustration. And most notably in the lower left-hand side, you see the electrical connector, and that's not multi-wire. You're going to get a coaxial type of connector, and when you look at that across the room, it's a pretty good bet that you've got a single axis piezoelectric accelerometer. And that connector is wired to the circuitry inside, but we'll get back to the center of it. In the center of this, we have the mechanical ground, and you see that as the gray post extending up through the middle of the device. And then immediately after, the bronze color element in there, that's the actual crystal. Okay, in this case, it's a annular shear crystal. And then we immediately outside of that, we bond a preload ring. Okay, let's see here. Yeah, the preload ring is outside of the seismic mass. So you have 3 layers. We'll talk about 4 layers. The first layer is the mechanical ground. That's the post of this accelerometer that you see in the middle. The second layer is the piezoelectric crystal, which is that bronze type device. The third layer is gray. The third and fourth layers look a lot the same. You can't really see it that well. But it's immediately next to the crystal is a seismic mass made out of tungsten usually, almost invariably, and it's used because of its high density. And that seismic mass is held in place in this case by that preload ring. And the preload ring is a material specially designed to apply very repeatable deformation when it's usually when it's heated or treated in a certain way, and then when the heat is removed, it contracts to clamp all of that mechanical structure together. And it's a one-time set type thing. So if that temperature is applied again in the future, we don't get another loosening effect of that material. It stays tight, and that's unique to that material. And then, so we get on the bronze section there, we get charge collecting on one side of the crystal, and the other side of the crystal is the mechanical post, and that's our mechanical ground and also our electrical ground of this accelerometer. And those are wired to what's at the top there, an ICP microelectronic circuit, and that is that's used to convert that high impedance signal inside the sensor to a low impedance signal. And we'll talk more about that later and why that impedance thing is important, because just inherently we can, at this stage, we can kind of intuitively see that it doesn't make sense that we get this voltage generated by this crystal, but it's kind of intuitive to not think it's not a very high power type thing. It's not generating a lot of current to create a high power type situation. It's a nice voltage output, but it's not going to be driven over long distances or long wires. We can't generate that kind of charge flow, electron flow. So one of the first things we do in the middle of this, as soon as we generate that charge across the crystal, we get it into basically an amplifier inside the accelerometer. that converts it to a low impedance signal that can be used to travel over long distances. Okay. And the characteristics, it's kind of like mimicking the ones we saw before on the low frequency devices. Dynamic events only. And when we say dynamic, we can go down to about 0.1 hertz with these devices. To get to 0.1 hertz, we'll talk about design trades later, but to design a 0.1 hertz piezoelectric accelerometer, it's probably going to be like the size of our fist, because we need more sensor output. We need more piezoelectric output, and we do that with more seismic mass. It has a wide dynamic range. Again, when we had 80 decibels before, this is 100 decibels. And that results in a 1,000,000 to 1 type ratio between signal and noise, okay? And that's, to use that same analogy, we never usually talk about measuring 1,000,000 Gs, but say if it's a sensor that's capable of a max range of 1 G for a very high sensitivity type device, it will have 1 micro G of noise floor. And that's a more relatable type example for this device. So these devices may have a range of 1 G and a noise floor of 1 micro G. Wide bandwidth, they regularly go over 10 kilohertz, even 20 and 50 kilohertz sometimes, 20, 40, 50 kilohertz. They operate over 2 wires, I mentioned that before, and they're very rugged. That piezoelectric crystal is very stiff. The mechanical ground is very stiff. And finally, the tungsten inertial mass is very stiff and very not brittle at all. They can withstand shock events and without incurring damage to the sensor. And there are high temperature versions. We go up to 1240F now, 650C, and that's basically a limitation. Well, it's basically a material properties limitation of the type of crystal that we use, the type of mechanical ground or housing that we use, and of course electronic components inside the sensor. But if you're talking 1240F, we're probably not doing an ICP. We probably don't have that circuit inside of the sensor. It's what we call a charge mode sensor, and we'll talk more about that in the coming slides. Okay, so piezoelectric sensors have a wide range of applications. The first thing, we kind of do 2 things with vibration measurements. We do monitoring and we do test. And when you're talking monitoring, we're usually talking about things that invariably they're things that rotate, mechanical rotations, and things that go out of balance and need to be rebalanced, and monitoring these rolling elements in machinery to make sure the bearings are healthy and predict when the bearings are going to go bad. And then another rotating type device is what you see at the top there, consumer goods, white goods they're called, a washing machine as you see there. Those are actually used in test. We actually, those product developers do testing for sound and vibration quality on rotating elements. So we're doing test on rotating equipment, we're doing monitoring on rotating equipment, and of course jet engines down below, we monitor the vibration on the jet engine in the bottom application. But we also do testing where we're not doing, test is more, the vibration can be in any direction rather than just the radial direction of a bearing. Those are the kind of things we talk about. And of course we have a list over there. We do this in the automotive industry, the aerospace industry, industrial machinery, white goods. They're used all over. And that's really the vast majority of accelerometers that we see out there. The mechanical design, okay, of this device. We talked about the electrical design a little bit. The mechanical design, these are words on the left that describe the mechanical strain that is being induced to generate the electrical signal. The crystal itself that you see there, that's the device on which it's strained, but that crystal will be cut in different directions in different parts of the actual raw crystal, the actual rock that you saw before. And this diagram shows how we can do things where we can get crystal segments that give us output due to a shear strain, due to a compression strain. And after that, this is really the 2 strain modalities we have, and then we assemble those into different mechanical configurations on the accelerometers, which we'll talk about next. And you see we have examples here of tri-shear, annular shear. These are all that shear mode, but they're all just subsets, specific mechanical geometries that we use, okay? So the beam configuration the beam element that we see here, what we see here at the base, the bottom of this diagram is again the base of the accelerometer attached to the structure we're measuring. And at the top, we get that fulcrum that's labeled there very clearly. There's the mass that's epoxy bonded to the top of it. So that's our inertial mass, and you see we have weights out to the side to make it more likely to flex. And we bond that to the crystal that's finally on the top, and that gives us the ability to do strain, surface strain on the top and bottom. The surface strain that causes electrical polarization on the top and the bottom of the device. And those two sides of the crystal are once again routed to a op amp and then routed outside of the accelerometer on a 2-wire interface. Okay, this is a very high output design. It's very low mass too, because we don't use a lot of tungsten in this design, almost none. But we don't use it very much anymore because what we found is, although it's very high output, and we all like a high output, high sensitivity sensor, that if you look at those two materials bonded right next to each other, that's a structure very familiar. In this case, it's basically a bimetal device, and what you see there is those bimetal devices, when they move from the left to the right, when we increase the temperature, when they're bonded together, they have two different coefficient of thermal expansion, and when they expand differently and they're bonded together, that induces a strain on those two devices, which is an output. And then when you strain a crystal, you're going to get charge output, and that output is not due to vibration, but it's due to the temperature. That's the effect we're seeing, and that's not so much an accelerometer as it is a thermostat. And that's one thing we found when we used these a long time ago, is that there would be, if we got into high thermal transient type events, when, say, we'd open the doors to an aircraft hangar or to a test bay in a dynamometer type environment, that inrush of air would change in temperature on the surface of the accelerometer, and we'd get output due to that temperature while we're taking data, vibration data, and it could wreck our test data. So we've matured more. The next maturation level is the compression design. That's what we see here, and again, you see the seismic mass on the top, and that's attached very tightly to the piezoelectric crystal directly below it. And you can see there, as the sensor moves up and down, we get compression and tension induced on that crystal. And that compression and tension causes electrical polarization, and we wire that again to the op amplifier on the right and back out of the accelerometer. That's been used as a very high frequency type design still, but it's a design we've mostly left behind for the most part, because it was used in the beginning because it was a very cost-effective type design. We were literally, when things were being manufactured on a lathe, that was our lowest cost machine operation. We could make round seismic masses and round piezoelectric crystals, and they all fit together very nicely. But a better design is what we call the shear design, which is, we'll come back to this diagram. And in this case, what you see here is the crystal is what we call annular shear. It's a ring, okay? But let's make sure that it's still the same, and that vertical motion up and down causes the mass to move up and down, and rather than compressing the crystal, it's shearing it on the inside and outside. So that's the annular shear, which indicates the crystal is in a circular configuration. And then the tri-shear version looks like this. This diagram shows this post goes from a cylinder, the mechanical post, to a triangle on the plan view. And we're able to put three crystals a crystal on each side of that triangle and a mass on each side of that triangle. It does a couple of things. It makes that mechanical post much more stiffer and drives out the mechanical resonance of the sensor, very much higher frequency. And it also gives us basically 3 times the output of the crystal configuration. So we like that because it gives us higher sensitivity, higher resolution measurements, and higher frequency too. So that's those are the basic mechanical designs we have. The next thing we'll talk about is the crystal design. So this crystal is kind of at the center of every one of these designs. And the 2 columns on the right of this table are the 2 basic material choices we have. Broadly speaking, we have different types of ceramic and quartz. Quartz is a natural material that we pull out of the ground, and ceramic is a synthetic type material that we have the ability to grow in a lab. It's a crystal that we can grow and culture. The ceramic crystal design is higher sensitivity inherently. We can build those so that in a given crystal cut, whether it be shear or compression, we have the ability to grow those crystals so that they have a much higher piezoelectric output for a given strain. They have the ability to go much higher in temperature also. That's the advantage of ceramic. And then on the other side, the quartz elements have lower thermal sensitivity. So if you get into a situation where you have, during the course of a test or a monitoring situation, where the temperature of the surface of the structure may vary widely, when it varies, it's going to a steady state, not a transient, a steady state change in base temperature of the accelerometer will cause a steady state change in sensitivity of the accelerometer. That's the thermal sensitivity. And that's much less measurable on a quartz element rather than a ceramic element. And finally, long-term stability. The quartz is superior. There's data over time that the quartz is stable. It stays the same compared to the ceramic. In the ceramic, we can see those outputs half-life. They can decay. Basically, the sensitivity of the accelerometer goes down over the long periods of time. And we're talking maybe 1 to 2%, but it can vary over the course of time, and it will invariably over time. Moving on to the electrical design, the first design we'll talk about for piezoelectric electrical. We go into more depth on these piezoelectric ones because it's the most common type. We have what we call charge output accelerometers, or AKA externally amplified. So I mentioned a couple of times before in the previous diagrams on the crystals, they are wired directly to an amplifier. That amplifier in the charge mode instance is moved outside of the accelerometer usually to move away from the accelerometer, to also move away from a high temp environment, because I think I mentioned that the most vulnerable part of that accelerometer is the electronics to temperature. And what we'll do is, most commonly we'll see it on the bottom there, we see that block that's called an inline converter. To do that, we simply move the microelectronics that were inside the sensor and move it out of the hot or high temp environment to that inline converter. And then the yellow line to the right of it indicates that we have a constant current, which we call a constant current signal conditioner, where what we do is we supply that op amp inside that circuit with a constant current, and that device, the signal conditioner to the right there, has a constant current diode in it, so that the current to the transducer remains the same. It's a DC current loop, and if that DC current is constant, that means the voltage has to change, and that allows us to measure a varying voltage that's directly output to the acceleration of the accelerometer. And then the other design you'll see up above, the diagram above, it's the same idea, but it's much less common. You'll see these laboratory style charge amplifiers that are very, very precision devices. They have lots of tuning on them. You can vary the gain. One thing you can do with any of these amplifiers, they can be built with different gains, different filters. And what that dark blue lab style charge amp does is let all that be variable, and you can tune that and use it in a wide applications. And they're very low noise typically, because they're just designed to be a very expensive type of instrument. And they're usually pretty high quality. And what you'll see below in that inline converter may be a much simpler circuitry, maybe higher noise circuitry, but it's also very lower cost circuitry too. And those both connect. There's constant current conditioners. The lab style charge amp is not constant current signal conditioner. It's more complex than that. Both its conditioners provide a low impedance voltage output that can be connected to a data acquisition system or a scope. And then this is where we talk about constant current, ICP or IEPE type devices. The little op amp symbol on the left on the sensor is way out on the left. That's converting that high impedance signal from the crystal to a low impedance signal very quickly inside of the structure of the accelerometer. And that blue box, we call those blue boxes traditionally from PCB, that's where we're talking about the constant current supply. It's the same thing. We use a constant current diode in there to maintain a constant current. The FET inside of the accelerometer induces a variable voltage. That's the dynamic voltage signal, and that's the voltage we're measuring of dynamic events, either after passing through a signal conditioner externally to the readout device, or in the bottom. Almost every data acquisition readout device has constant current signal conditioning built into it today. They can switch it on and off based on the GUI of the system, and it's very common to see that. What this does is that it allows the cabling to be much lower cost, much simpler, and much longer lengths. So we're not getting in a high impedance circuit, we're getting signal decay over signal and noise induction on the wire or on the cable over greater distances. And that just becomes a much lower impact type of noise than when we use the low impedance cabling and low impedance circuitry. Okay. So comparing the two electrical designs we have, on the left is IEPE and on the right is charge. Wide dynamic range of the charge mode accelerometers, and that's only in the case of the lab style amplifier. And that's what I talked before about that 1,000,000 to 1 ratio, or 120 dB. That's really possible when you're talking about a charge amplifier, one of those precision charge amplifiers with variable gain on it. Of course, I mentioned the hot environments, high operating temperature. Those are going to be the charge type accelerometers if you're working there. But on the ICP gives you the advantage of resistance to electromechanical interference, radio frequency interference. You're not going to get polarization and charge induced on those cables from those sources when it's low impedance. And it's resistant to cable effects. And when I say cable effects, cable length, cable motion, cable contamination, cables are just a much bigger headache with the high impedance charge mode systems. As soon as you convert that to a low impedance output signal, whether it's on the inline converter or on the lab style charge amplifier, you can run dozens, hundreds, thousands of feet of low impedance cable to the measurement device and there won't have an effect. That's not the case with charge mode cabling. You're going to see high frequency degradation, especially on those long cable runs. And finally, I've talked about a number of different, I used the word sensitivity at different times, and this gets into the calibration side of things. Finally, we talked about how these accelerometers transduct the mechanical energy into an electrical signal, and that's most recognizable in what we call the sensitivity of the accelerometer, the one number that we use to indicate how many millivolts output we get for 1 G of input. That's a ratio. That's just what we call the sensitivity of the accelerometer. And that upper oval that we've drawn on here shows what we call the sensitivity of the accelerometer at a reference frequency. And that reference frequency in the US is usually 100 hertz. In other parts of the world, it may be 159 or 159.1 hertz. But that's what we call the nominal sensitivity or reference sensitivity. And we pick that point, and what you'll see is when the spec sheet you get from PCB.com, it will have a line on it that indicates that the sensitivity of this device when you buy it from PCB is going to be, for example, 10 millivolts per G plus or minus 5%. And that sensitivity means the reference sensitivity, usually at 100 hertz, and that can be, if it's plus or minus 10%, it can be from 9 millivolts per G to 11 millivolts per G, and PCB is going to accept that, and it's going to be a passing calibration qualified for external use and shipping to a customer. 5% is going to be less than that. It's going to be 9.5 to 10.5, but that's what we mean by a reference sensitivity. And then there's also the frequency response specification, which you see on the bottom. That's we usually chart that, and the reason we do that frequency response test is because it's the most effective way to find defects in an accelerometer. That's the most common way, right? So we've been building these accelerometers for a long time. The industry has been building them for a long time. And what we found is if we do a successful frequency response test on an accelerometer, the rest of the characteristics of the accelerometer are probably good also. We use this frequency response specification to indicate the change in sensitivity over the operating frequency range. And one of the great uses or characteristics of accelerometers is that they operate over a wide frequency range, and we happen to want to make measurements over a wide frequency range of our mechanical structures. So that's a specification that you'll also see on your spec sheet at PCB.com. That's called a frequency response specification of, say, plus or minus 5%, and that's really a percent on top of a percent. Okay, so you'll see a percent specified for the reference sensitivity, and then we do a frequency response test to basically measure how flat it is over a frequency range that may be plus or minus 5%. but that 5% is reference to the measured sensitivity at 100 hertz, not the nominal sensitivity of the perfect 10 millivolts per G that is the nominal that you see on the spec sheet. They have different specifications, and they're different. When we say those percentages, they don't mean accuracy or uncertainty. They're just pass-fail tolerances for that accelerometer at the factory when it's born, on its birthday, and then also when it's recalibrated. So that's what the calibration of the accelerometer looks like. You'll get one of those from PCB when it rolls off the production line at the factory. And that shape of that curve, that flat line that we see in that chart on the previous slide is shown here. And what we see is the flat frequency range is in the usable frequency range is the flat part of the curve in the middle of this spectrum. And then what happens at high frequency, it displays the behavior of a very classical second order mechanical system, a spring mass damper system that we see there on the right. And we see the C value, the damping value, is typically very small for these crystals. They're very, very lightly damped. And then what that leaves basically the mass at the bottom and the stiffness of the spring. And the mass at the bottom that's equivalent to the inertial mass that we talked about before. And if that inertial mass is higher, that resonant frequency comes down, square root of K over M effectively. And that's what governs the high frequency response of the accelerometer. And then at low frequency, you see the curve to the left. It shows a roll-off, and that should look very familiar to this. It's a first order electrical system, right? So it's the electrical characteristics at low frequency, the electrical components that we choose that show the low frequency response, and at high frequency, it's a mechanical type limitation. Okay, and then we start talking about how we make these trades of what kind of sensor we're going to design. And that's what we're trying to show on this slide. What you'll see on this slide is at the upper left, let's take away the first bullet, okay? The design trade we make when we design accelerometers is we have to balance the sensitivity that we want versus the high frequency response, right? So the perfect accelerometer has very high sensitivity, and it also has very high frequency response, but we can't have both of those inherently in a design, and we frequently trade off because of that mass, that second order system that we talked about on the previous slide. What we do is when we put a large mass on there, that's more inertia acting on the crystal, which causes more polarization and more signal. And in the upper left over here, you see that 100 picocoulomb per G curve. That's very high output, that's higher sensitivity. And then, but also the resonant frequency in the flat part of the frequency response also pulls it into much lower frequency. So we have inherently high sensitivity accelerometers are also going to be rather low frequency type devices. And the low sensitivity accelerometers are going to have extended higher frequency range, okay? So the other thing, not only does the sensitivity change, but those are, as we go higher in frequency, it's a lower sensitivity. It's also a lower mass because it's literally the difference between a sensor that weighs 5 grams or a sensor that weighs 200 grams possibly, right? And it's a design trade that works out application specificity, because what we'll find is on structures that operate at very high frequencies, the acceleration levels are also very high frequency. They're also very high level vibrations. We want to use on those structures, they're usually very lightweight structures with high frequency activity. It works out to our advantage that we have a lightweight sensor for a high frequency application on a very low mass type structure and a very high resonant frequency of the accelerometer. Those things kind of go together, right? So the curve on the lower right, that's an accelerometer in an application that may be a computer hard drive. Very small device, very high frequency, not very able to tolerate a large mass when we place an accelerometer on it. But on the other end, on the left-hand side, a 100 picocoulomb per G accelerometer is going to be very heavy. And if we want to use a very heavy device, we want a very large structure like a bridge, okay? And on the bridge, you can tolerate that high mass accelerometer, so it doesn't affect the vibration of the bridge, but also the vibration of the bridge is also going to be very low level, so we need the high sensitivity of the accelerometer to draw that signal out of the mechanical motion. The walkway is basically we have to trade sensitivity versus high frequency response. The other bullet we could put on here is that we trade mass for high frequency response. So we give up, if we want high sensitivity, we also have to tolerate higher mass. Finally, frequency response effects. So we have different frequency response effects on the previous slide. We're here, we see the effects of frequency response due to the design of the accelerometer. And then that frequency response is also affected by the mounting of the accelerometer when it goes to the test structure. and also when it's mounted on the calibration system. And what you'll see on these curves, starting on the right-hand side, we have in the upper diagram, we show the mechanical mounting of the accelerometer. And number one is what we call stud mount. And that's where we tap a hole in the structure we're measuring, and we use a mounting stud to connect the torque down the accelerometer as tightly as we can and make it attach as rigidly as we can to the structure. And we have that same number one is also mentioned in the lower plot that shows the frequency response, and that's the best high frequency response characteristic. And then moving to the other end, the hand probe type configuration on the left, that's more of a loose, there's opportunity for a lot of relative motion between the structure and the actual accelerometer of that configuration. And that results in, although this accelerometer may be capable of that 20 kilohertz response, that's going to drag down the effective frequency response of that configuration, with the mounting configuration, down to 1 or 2 kilohertz. And what we show here is that what you'll get, your spec sheet from PCB is going to be based on most likely the one on the right, because accelerometer manufacturers want to give the best case for their accelerometer, assuming the users mount it in the best way possible. And they're going to calibrate it in the best way possible too. It's the stud mount characteristic, the stud mount configuration is the most repeatable type of mounting you can use. But we bring this up from a calibration point of view because there's two kind of philosophies about calibration when you're calibrating accelerometers. You may want to calibrate it exactly the way it is at the factory to check back to make sure it hasn't changed since that factory calibration, and to determine the sensor health, if you will. The other philosophy could be used much less often, is not being concerned so much with the original specifications of the accelerometer, but we may want to calibrate it exactly the way it's used in the test environment, where it goes out, after it leaves the cal lab, goes out to the test engineer, he puts it on his structure, and if he's putting it on there with a magnet or an adhesive mounting pad, that engineer may want to have it calibrated in that same configuration to know what real frequency response they're getting, as opposed to the optimal response that comes from the cal lab. And that's an option sometimes, used much less often, but that's the mounting configuration effect on frequency response. So kind of wrapping this up, we have 4 rows in this, and we've talked about element design, mechanical design, crystal material, and electrical design in this presentation. And what we choose, and we'll talk about the choices we make in designing that reference accelerometer. In element design, we choose piezoelectric. And the reason we choose piezoelectric is because it is not affected by the excitation voltage. That's one thing. It's very stable. It's very low maintenance. It's hard to really change the performance of a piezoelectric accelerometer once it's sealed in its hermetically sealed laser welded package. And we choose piezoelectric, and it's the most reliable in that regard. On the mechanical design, we choose a tri-shear. That's just a lot of times the default design. It's the highest resonant, the highest frequency response mechanical design. And you may be able to get a cost advantage by going with an annular shear compression design. But when you're talking about a reference accelerometer, it's kind of like a special accelerometer. You're not going to buy dozens and dozens of reference accelerometers to do a test. You're going to buy one accelerometer. It's going to be a reference to all the other dozens of accelerometers you may have in your operation. So it's worth spending a little more for in that aspect because you're only buying one of them. The crystal material is quartz rather than ceramic. Mainly, the main strength is the quartz stability. I mean, that's one advantage. 2 advantages of ceramic are the high temperature environments it can do. We're going to be working in a lab. We don't have to deal with high temperature environments for a reference accelerometer. And also is the high signal output of a ceramic. But in this case, we're calibrating on top of a shaker. I mean, it's really a high signal environment anyway. So the advantage of ceramic over quartz isn't really relevant when you're sitting in a very temperature stable laboratory on top of an electromagnetic shaker where you've got lots and lots of signal. And finally, the electrical design. We use the IEPE, aka ICP design, as opposed to charge. And we do that just to get the consistency. We don't want an operator to have the opportunity to change a filter setting or change a gain setting on a lab style charge amp for whatever reason, or to not even change it, but to use it when it's not set correctly. There's just too many things to make a mistake on when setting up a charge amplifier. So we use IEPE for very consistent, very repeatable type devices, measurements which we're making on a calibration situation. So that's how he uses, that's our overview of the different design characteristics of accelerometers, and finally why we make the choices we make for a reference accelerometer. We come together next time, we'll talk about calibration techniques and how these reference accelerometers are used in calibrations and the actual calibration techniques themselves. Thank you for joining me today. I hope you have questions. I hope you enjoyed it. We'll get my contact information out there too. If you want to follow up with me directly, I'm happy to talk with you. Happy to get on an email with you. Thanks for coming, and take care.